Welcome, everyone. So this is our second week reading Understanding Deep Learning. So last week we talked about linear regression, and this week we are looking at shallow neural networks. So the chapter starts off kind of defining what is a neural network in math terms. So they show here's the various parameters, and we'll look at this in more detail. I made a Jupyter notebook that I'll share later when we're looking at that. And it's this kind of interactive look at a neural network. So you can play with changing all the parameters and seeing how it affects everything. So I won't dig into these in too much detail, but they talked about the parameters. They talked about activation functions or nonlinearities. So for a lot of this, they were showing ReLU, but at the end they have all of the different um, options. There's a bunch of different things that you can plug in there. Um, and so they show the ReLU function. You've got your input and it's getting thresholded at 0, and then anything beyond that is just directly passed through. And so if you have a shallow neural network, you can kind of compose this into multiple different linear equations that are kind of contributing different amounts and yield a different output for you. Um, and so part of the chapter, they show kind of decomposing the problem into multiple different equations and pieces. And I think that this is interesting, but I think that it's actually more fun to just play with the numbers. So I set up this notebook that I will share. It's on Colab, so everyone should be able to just open it up and run it, and I will drag it over there as well. So the funny history behind this code is 7 years old. It was one of the first things that I did, like machine learning related. I was on Upwork and someone paid me essentially to make this little neural network animation thing. And so we're using something that I haven't looked at in forever, but I figured I would pull it out just as something fun. Um, So this is using a very similar visualization of the neural network that's in the book, but we can kind of move all these sliders around and just see how it impacts things. So right now we have two inputs. We have x1, x2, and then we have some output. And right now it's 0 because all of the weights are just set to 0, so nothing's getting passed through. So we can start by just making that first connection. Um, and so we can set this to any value that we want. Um, and so like I'll just put it at 0.5, and then you can see this is passing we've got the one input, we multiply it by 0.5, and then it's ending up at this neuron, and it comes in at 0.5 and it leaves at 0.5 because the ReLU just lets it pass straight through. But if we did something different, like if we made this negative, um, now we're doing 1 times negative 0.3, and it's going in as negative 0.3, but it's coming out as 0 because the ReLU actually thresholds it at 0. So now no information is passing through to this next connection. Um, and then we can make our final connection that is from the hidden unit to the output unit. And so setting this to 0.5, we can see that it's the output from this hidden unit is actually 0, so the 0.5 doesn't yield anything. We need this value, this neuron, to actually activate in order for anything to pass through. So for example, now that it's positive, we can see that stuff is actually passing through this neuron, and then it's going through this whole path of 1 times 0.2 gets passed over here, and then 0.2 times 0.5 ends up 0.1 all the way at the end. And so we've built our kind of first linear system here, and we're just letting it pass through. But then we can go and we can add in, like, let's add in some value from x2, for example. Um, Gotta remember which one is which, this one. Um, So now we have some positive contribution from this as well. So now it's 1 times zero point 0.3, and then this gets summed together with the contribution from over here. So instead of being just 0.2, it's 0.2 plus zero point 0.3, and we get 0.5 here. And then we can see it reaching all the way at the output. And we can go through and we can change a bunch of these values and just see how this goes. Um, and so you can see as this contributes to this neuron and this contributes to that neuron, and if this one was strongly negative, then this value might not get passed through at all because this one contributed so negatively and it ended up as a negative value, and then the Rayleigh function thresholded it away. Um, and so this is kind of just a way to play with the numbers and understand what is actually happening with all of these connections. Um, and so one important piece to this is you can look at this as individual connections, but the way that most people look at it is a matrix multiply between these. So we have a two values going in, and then we multiply that by a 2 by 3 matrix that's representing the two inputs going to the three middle neurons. And then after that, we have a 3 by 1 matrix that's going from these three neurons to this one neuron. So we're just doing a couple matrix multiplies really in order to get this information passed all the way through. But if you decompose it like the way I was, you can look at it as like let's just trace the path from each neuron to each other. But most implementations, um, you'll see it's just a matrix multiply. You won't see um, actually doing all of these operations manually like that. Um, I can pause there if anyone any questions on this.
I have a question. So I know like in deep learning, ReLU activation function is like almost like the gold standard, right? But and the reason to use this instead of like I think sigmoid or other previously popular is to get rid of the vanishing gradient when the value is getting large or extremely small negative numbers. So have you guys tried like any other alternative? Like I heard like leaky ReLU or there are a bunch of alternative that so that in ReLU you have zero slope when the input is negative. So my question is, will that also pose problem given the negative input that you have zero gradient and then in terms of training you may not be able to train further in that case. I don't know if I even make sense or not, but
Yeah,
just my
yeah,
question. Yeah, yeah.
yeah. I understand what you're saying. Um, so it's possible for that to become a problem, and that's the whole point of leaky ReLU is they realize that you can have these um, gradients that just completely get set to zero, and the neuron's basically just dead at that point. You can't learn anything on it once it gets set to a value like that. And so people have experimented with many different activation functions. There's GitHub repository I know of that has like 70 of them, and it's just benchmarked for um, ImageNet with all of these different activation functions. Um, and my my opinion is that it seems like regardless of what's actually happening within the neural net and the activation, it doesn't seem that important in reality. People can get very far with just ReLU or leaky ReLU, and you don't have to do anything much more complicated than that. Um, there are marginal gains in performance, but very rarely is it the difference between a good model and a great model. It's just a small 1% gain. And some of them can have better convergence or faster to calculate, or so there's a bunch of options and there are trade-offs to a lot of them, but ReLU is a decent starting point. Leaky ReLU maybe even a little bit better.
Hey Ryan, if I could just kind of add on to what you said too, I think like
Yeah.
another big thing about in practice is that it's really hard to beat computational cost of ReLU, you know? So again, like some people might argue for that 1%, but it's very rarely worth the cost in computation to switch to like CELU or ALU or something like that, you know? So usually that's why people use, to answer the original question, that's why people usually always use ReLU. It's just, it's very, very cheap.
Yeah. Any any other questions on this?
So I'm assuming the hidden unit two, the RailU is being applied there, right? On all of these.
Yeah.
I'm
Yeah.
just the negative number there, negative 0.8. What does that correlate to?
So this is the weight. So this is the
Ah,
actual activation. So this is saying what is at this neuron, and then the
okay,
weight is saying multiply the 1.9 by zero point 0.8, negative zero point 0.8 on the way out.
gotcha.
So if it was zero point 0.8 on the way in, then it would get set to 0. But because this is the output weight, it can be negative and it still gets passed through.
So
Okay,
I'm not
thank you.
understanding the difference between the P1 and the Z1 because they're both 1.9. Yeah, and all of them, it looks like P1 and Z1 are the same value.
So that's because all of these values are positive. So um, let me change one of these. Yeah. So now this one is red, which means that it's actually getting thresholded. So the ReLU is saying zero point 0.3 is going in, but then it's 0 going out because it got thresholded to 0.
Negative 0.3, you mean going in?
Yeah. Yeah.
Yeah,
Negative 0.3.
I see. Okay, so the Z1 is what happens after the activation function.
Yeah. Yeah. The
I see.
P1 is the pre-activation and the Z1 is the post-activation.
Okay. So in this case, no matter what you do, Z1 is either going to equal P1 or it's going to equal 0, right?
Yeah.
Okay.
Yeah, exactly.
Is there an offset here? Seems like we're just multiplying x1 with a number uh, when it comes into the neuron.
So in this case, I don't have a bias term in there.
See,
So that is where that would get introduced, but that would basically shift some of these thresholds around.
okay.
Okay, if I can ask, I don't know if it's somewhere in the book, but um when I train the neural network, because like we all know like we're using like gradient descent. So gradient descent is trying to find the ideally global minimum, but in reality you might have local ended up in local minimum. So I'm wondering like you guys any experience like do you when you train a model, do you start it out with different initial value and that is fine if let's say 10 initial different values and that 10 of them I mean that find a 10 local minimum and compare which one has the best among the 10 or how do you guys deal with this like local minimum stuff?
In reality, with neural networks that have enough parameters, it isn't commonly a problem. So you can break out of whatever local minima. Um, so people have done studies on different initialization strategies and trying multiple initialization strategies and picking the best one. And it's another one of those things where it matters, but people have found reasonable defaults, so it's all right to just take the defaults that people have figured out. So like you don't want it to be all zeros or all constants. You want it to be probably just basically small random noise, and sometimes the amount of noise is scaled based on the number of parameters or inputs or outputs. So people have figured that out, and those will generally do reasonably well. And as far as doing multiple initializations and multiple runs, some people can do that if they're really trying to hack the last few percents out. Like in Kaggle competition, sometimes what we do is we just change the seed and then that will change the initialization. And you know that your model is going to be a little bit different from the previous one. And then you might average all of their weights together or average their predictions together, and you can go further with that. But in general, you shouldn't need to do that. Most models will train correctly. It's not going to get stuck in a local minima and be some terrible result.
I think Glorot 2011 is a good, I think that's the first kind of topic on initialization. That's a good paper to read for historical reasons on initialization.
Yeah. Yeah.
I had a question about um, the linear regions. So if you had one input and three hidden units, I think it's like you have three joints and then you have four regions, right? How does that change when you have two inputs? And I guess what's the intuition about why that's more powerful?
Um, I'm less knowledgeable on that. I don't know if you have any input, Ted, or anyone.
So, so the chapter does talk about this. It's difficult because normally when we have two inputs, what we think of that as being a point in two-dimensional space, in XY space, okay? And if you have three inputs, we normally think of that as a point in three-dimensional space, okay? Once you get past three, it's like, how do you visualize it? How do you think about it? It gets gnarly, like really, really fast. Okay. But if we start with just two, the book kind of talks about basically instead of in the one-dimensional case, you think of it as this ReLU shaped thing, right? Part of it's horizontal and the other part of it goes off on an angle. So it's, for lack of a better word, a V shape. It could be a very wide V, or it could be pointy V, but it's kind of a wide V shape. So once you go to two dimensions, what you now have is like you take a piece of paper and you put one fold in it. Okay. So instead of it being a line, it's a plane that has one fold in it. And then as you go into higher dimensions, it's still going to be like whatever, n-1 dimensions with one fold in it. And so that's where the book shows that, like, hey, if you had three of these with just two inputs, what are the different ways you can combine three like folded pieces of paper? And the diagram in the book we can look at has them where they're coming from different sides, and then I think it's like a bigger 3/8 or something like that. And so they form kind of a triangle in the middle. Okay, it's a little hard to visualize, but yeah, if you keep going down from there, when you combine those 9 things, then you get that one, figure J. So the idea is you have this triangle in the middle, and then things are sort of sloped away from it. And if you look very closely, you'll see the one in the middle left is actually flat, because that's the one where all the flat regions of the 3 pieces of paper intersect. And so I don't know, for me, it's geometrically hard to really extend things, but the idea is that whatever the dimension of your space, you are still chopping it in two every time you do something. There's, left and right of it, above and below it, whatever you want to call it, And so essentially what you're doing is you're still combining things that chop things in two. And if you have enough dimensionality, then they can all sort of keep doubling the number of regions, But if you limit the number of dimensions, eventually you can't keep doubling things, right? So it's like if I have a pizza, and the first cut I can make twice as many pieces from 1 to 2. Second cut I can cut twice as many pieces from 2 to 4. But the third cut I can't get 8 pieces, not within just 2 dimensions. Okay, so that's why if you look at the curves in the book, it flattens out. It's not just pure exponential doubling with every cut. I don't know if that helped answer your question or not.
Yeah, I think so. Yeah, I think this book, yeah, it's really helpful. I think the approach that this book is taking is really helpful. The fact that it's started with the functions before showing the neural networks with the circles. So I think that really clarify things.
Yeah. All right. Thanks. And then maybe when we do the problems, there'll be a couple other aspects of this that kind of get reinforced. We'll see.
Yeah. So this is, I'm bringing this up because it's kind of related. So this visualization, I didn't find this very intuitive. It's a bunch of lines and colors, and I didn't really piece together exactly what was happening. And so I don't know if it will work in the notebook that I shared for everyone else. I was having trouble getting it to work in Colab for some reason. So I have this visualization over in VS Code as well. And so what this one is doing is it's kind of recreating what's in the book, but it's actually in 3D, so you can see the shapes and what's happening. And this is kind of reusing what was in the other one. So we can take our parameters and we can actually change them, and we can see how that changes the surface that it outputs. So I swept through from inputs of -2 to 2
Wait,
on
sorry,
both.
and Ryan, I just want to clarify what this is. So what this is on the X dimension and the Y dimension, those are the two inputs, and then the Z dimension is the loss function. That's what we're looking at.
It is the output of the neural network at this point.
Oh, okay.
It's
The Z
not
is
it's
the
not
output of
loss
the
yet.
I see.
Yeah.
I see. Okay,
Yeah.
cool. And then what
So
are the colors? I see a color bar on the right.
this is, I mean, this is to show the value of the output. It also
Okay.
scales the color
Okay.
on
Okay.
that. And so this is sweeping from -2 to +2 on X1 and X2, and then the Y value is what the model actually outputs. And we can see right now, regardless of what you input to it, it's always just going to be 0 because all of the weights are 0. So it's just this flat plane right now. But if I give it a little bit of value, you can see nothing happens because it still doesn't have a path all the way to the output. The rest of it is still set to 0. And so if I set this up, we can see now, okay, now that's its first ridge. We've got a kink in our graph. And so now we can say, let's add some value to something else. And we can see, we can build all kinds of different shapes, and we can see the various different faces of it. So you can see that there's actually multiple different kinks in this graph now. And so we can keep building that up and build a bunch of origami out of it, basically. And so you can play with this and see how things interact. And so you can do the same thing that we saw in the previous one, where if this one has a large enough negative contribution to overpower this one, then it will just end up looking flat, and you don't actually get to see any value coming in from this neuron. So this is just another way of visualizing, I keep losing it, this thing. It's just showing it in 3D basically. So you can actually see the slopes and the kinks in the graph and everything that's going on there.
Yeah, that's cool, Ryan. So hopefully, like when you added that first one, you could see what I was saying about a piece of paper that has one fold in it. And then if you intersect two of those, it's a little bit hard to see, but if you look closely, you'll see that like different parts of the paper that are going up, they're not all the same. There's like you said, a kink in it. Some of it's going up more slowly, some of it's going up faster, steeper.
Yeah, thanks for this. It reminded me of the first time I saw that like a decision tree on a XY plane, and it's also like splitting up like the input, but this one seems more flexible with diagonals.
Yeah.
Yeah, that's a great analogy. So if you've seen that visualization for decision trees, you have a constant value in each section that you split. What's a little bit different, I don't know what other adjective to use here, is that one half of the split is flat, but the other half of the split gets to just be a continuous slope.
I'm trying to see if I can find the decision tree thing really fast. Maybe
There's
I...
actually a problem at the end of the chapter, Ryan, that I think really addresses this concept. So whatever,
Yeah.
when we get to like problem 14 or something, that'll be a
Alright.
good thing to talk about.
I will save it then. So I think those are kind of, those visualizations I think explain a lot of what's in the book, just understanding the flow of information and the nonlinearities, and then the different regions and faces that it will create. So on top of that, there are also so this is what Ted was mentioning, where as you go up in the number of in units and parameters, it will plateau off eventually because it doesn't scale linearly. And here's the splitting across the planes. And I think that's it in terms of the contents of the chapter. Here's all the activation functions. So not all of them, but these are many different options, a lot of the common ones.
We have several chapters coming up talking about training. I have not read the whole book, but it's going to get into the issues of how to make training work. I'm confident, so I think we'll get into it a little more detail.
Yep.
Can I ask a question? So this is like, for example, like at business setting, when we build, like, for example, let's say, for sake of illustration, we are working for a marketing, campaign, and there are, of course, several potential predictor or whatever you want to call it. So when, like, for example, traditional statistical model like linear logistic regression, let's say this case we would build a response model, who will purchase versus who will not. So logistic regression is easy and simple enough, and the best part of using this traditional stuff is when we meet up with the business partner, we're able to, like, tell them right over there, like, which factor, if you increase by how much, the result will give you 10% increase in whatever, right? Likelihood of respond or whatever. So in terms of neural network, I know it's like in this chapter is universal, approximation theorem, basically saying like approximate any whatever complex function you have. However, in reality, when we deal with business partner, like, it's, I don't know how to explain this to them, even though it give you a better, prediction or whatever. So in your experience, is there a way to, like, sort of open up the black box and kind of explain the best we can to, like, let's say business partner with no technical, expertise whatsoever? So explainability is what I'm shooting for. So if you guys can, give some insights, they will greatly appreciate it.
There's various techniques to try and get better understanding of these black box algorithms. One of the really popular ones is called Shapley. And so that's a method that will try to get back to that sort of contribution of each feature again. that you get from linear regression. So like for linear regression, you just look at the coefficients and you can see here's the correlation that's found basically. But Shapley can kind of try to explain that in a similar way. So that's one way to look at it. There's Shapley and there's Lime and there's a few other things. Um, what I tend to see is there's kind of two different modes. Some people model in order to get an explanation, and some people model in order to get an outcome. And I prefer to try to keep those separate because it's one thing to try and explain some phenomena or what's going on with the world versus I just want the highest accuracy for this given thing. And those worlds are often at odds. So if you can separate that and say, okay, here's linear regression in order to explain some of the relationships that we found, and then on the other side say, but we're using this more advanced model because it gets us 10% better accuracy. Um, Sometimes that works, sometimes that doesn't. It just depends on if people are willing to lose little bit of visibility on some of that stuff.
Yeah, I can add, I'll try to be brief that, explainability, interpretability is now like a whole subfield within machine learning. So there's a lot that you can do there. I think if you Google, what is his name? Christopher Molnar, he has like a free online web book that does a pretty good job of explaining a lot of these things. But I'll just highlight, there's, I think, 3 different techniques that people generally use in terms of interpretability. So one is local interpretability. So that's saying, hey, for this particular person, I made this prediction. And then local interpretability says like which inputs would change the most. So it's like, hey, if you had more income, that would be the biggest thing that would have improved your score on this. Or if you had fewer credit cards, that's the biggest thing that would have improved your score on this. So that's what local interpretations do, right? Global interpretations like SHAP can kind of say, like, overall, this feature is really important. And, higher income tends to improve your score, but maybe gender improves your score, or maybe, whatever. And then there's also things you can do that are sort of like uh, plumbing explanations, but without necessarily the specifics. So for example, in computer vision, people do say like, hey, at the lowest level, the model is looking at things like lines. So it can know the difference between a vertical line, a horizontal line, a slanted line. It can detect textures. And then it builds those up so that if you combine certain things, you can detect triangles, you can detect circles. And so ultimately, if you combine those things, then you basically can build like a nose detector, an eye detector, a mouth detector. And then eventually you combine those, you can build a face detector, blah, 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 blah. So that's not necessarily really telling you numerically what's happening, but at least it gives them an intuition of like, what is this mysterious, vision model that you have? You just say it's building these features from low level features up until higher level features. You're not actually saying that like, hey, this model actually is looking for, when it's finding a dog head detector on the left plus a tail on the right plus 4 legs, or a head on the right and a tail on the left. A car is composed of wheels on the bottom and windows on the top. Like, you're not giving that level of detail, but at least you're giving them some reassurance that this is the nature of the plumbing, not the specifics. But I'd recommend I found that website. I can go and Google it real quick and give you the link, but it was pretty readable.
There's a question about is Shapley for local or global explainability?
It's actually a little bit of both. You can use Shapley on an individual input for local explanations, and you can average SHAP values across a large data set for more global explanations. That I don't know how helpful that answer is, but it's kind of both.
I've I've run into scenarios with Shapley where it just doesn't quite seem correct. And it's supposed to come with all of these guarantees, but I just think that kind of credit attribution in all of these is still difficult. It's not really a solved problem. People are still trying to understand neural networks, and there's just a lot of open research on it.
I got a quick suggestion. So I'm coming from non-technical, I'm going into more technical, learning data science. And so I will say, you know, if we're talking about business and presentations and you know, having those conversations, I'd be curious about the audience. A lot of the time when I'm speaking to senior management, they're not asking questions about how this algorithm works. They're really looking for what the return is going to be. So I'll throw that in. But the suggestion is I've used ChatGPT and I've asked it for analogies for certain algorithms, and it gives you something pretty useful. Um, so there's that as well. It'll make up like a story to explain how the algorithm works. Like you have a set of friends and you bring in a friend, and then what was it? I think it was describing weak and strong learners, and I can't remember the algorithm at this moment, but it'll create a story. So that's been useful for me.
Yeah, that's
Yeah.
cool. And that's like sort of a plumbing analogy. But like if you work at a hospital and somebody says, why did you say Mrs. Jones doesn't get this procedure? You know, that's like a very different world from if you work for like Wayfair and you're just trying to sell more couches. Like they really don't care why it works. If you're like, I implemented this and the click-through rate increased by 3%, no one's going to ask you how the model figured that out. It's just like, I'll take the 3% in the bank and never ask you a question.
Yeah, yeah.
Yeah, the domain definitely matters, and the stakes, and understanding what the implication is for a incorrect prediction. I think that's something that I always try to do, is if you look at things in terms of a confusion matrix, what is the actual cost of a true positive versus false positive versus false negative? Because there's typically a cost associated with it. So if you overpredict something and that's making it so that someone has to do an action because of that every single time that you raise a false positive or something like that, that might be bad, or it might be good. You might want to make sure that you have 100% recall and you get everything and you don't miss anything through your filter. But it's just important to look at the actual like real world scenario and understand what the impact is going to be for incorrect predictions.
I have a very simple visualization of neural network as corporation chain of command. And if you need to explain it to some people like laymen, then I hope it is not very mathematical. I did use equations though. But basically it shows that you can view neural network as actual structure incorporation, and I hope it explains why they're so complicated, because when you have just few nodes, then it's more or less simple. But when you have a lot of nodes, then, well, how could you can explain why corporation does this and that? Quite often it is lost in these layers of managers.
Thanks.
Thanks,
Hey, Ryan,
man.
I was thinking maybe we pause here and we transition to the problems, just
Sure.
given time.
Sure.
So with this new thing, that actually means stopping the recording and starting.